I said that everything, in some sense, that was done for centuries after Newton was filling in the details to F equals ma. I don't want to give you the wrong impression. There are a lot of fascinating details. Newton's universe is rich and wonderful, and centuries of work by many, many, many brilliant people went into producing insights and understandings, and I wish I had the time to tell you about at least that part of it that I know. But we're in an astronomy class. What I'm going to do in the next two clips is give you sort of a highlight reel of those of the aspects of what has been learned in the 250 years since Newton and a little bit of the century since that will impact what we do and that we will need, and we will go through and try to develop, if not as deep an understanding as we did for gravity, which will be central, some intuition and some understanding for some other important concepts in physics. And as I said, we'll organize it by the M, the structure of matter, and the F, the forces that act. And we will start with the M side. We'll start with what we know about the end of the 19th century about the structure of matter. By the end of the 19th century, we have a pretty comprehensive understanding of the structure of matter, and its center is what is known as the atomic theory of matter. All known matter is made up of 100 or so types of atoms, immutable units. They're indexed by a number called Z that runs from 1 to whatever 100, and roughly high elements with higher Z have heavier atoms, more massive atoms, and these characterize the chemical elements. We understand some rules by which they bind together to form compounds and molecules and various kinds of objects. And bulk matter can appear in one of three common states. We have solids, we have liquids, and gases. And in each, the bulk properties are understood as a consequence of the microscopic dynamics of the atoms and the molecules that form it. And as a good and very helpful to us example, one of the forms of energy we discussed when we talked about non-conservation of mechanical energy was heat. Friction, for example, converts kinetic energy to heat, and heat causes an object's temperature to rise. So we know what we mean when something is hot. We mean it has a high temperature. In the context of an atomic theory, we have a good understanding of temperature. Temperature is simply a measure of the average random motions of atoms and molecules inside an object, which explains why heat is sort of the lowest common denominator of energy. Heat is the energy that something has when it's doing its own thing. It's not moving in bulk, but its own internal degrees of freedom are randomly fluctuating. And for example, in an ideal gas, that's a gas that's made up of atoms or molecules that have no internal degrees of freedom and are just non-interacting and bumping off each other in the walls, then you can show that temperature gives you the average kinetic energy of a molecule or an atom or whatever it is proportional to the temperature. And temperature in this expression is measured in Kelvin. Kelvin degrees are the same as centigrade degrees. That just determines the units in which we measure this constant here, K, which is called Boltzmann's constant. What is not arbitrary, of course, is where you put the zero of T, because doubling the temperature relative to that zero involves doubling the energy, and there is a temperature at which the average kinetic energy of molecules descends to complete zero. This is absolute zero, or negative 273 or so degrees centigrade, and this is the origin of that. And using these equations, you can see that at higher temperatures, the molecules bump around more. A gas exerts a pressure on any container in which you put it. The pressure is a force per unit area applied equally in all directions, and the pressure times the volume for an ideal gas is given by that same Boltzmann constant times the temperature times the number of atoms in this gas. Most gases are not ideal. There are all kinds of subtleties here, but the essence of what we see here is the temperature is a measure of the random motion of the atoms, and that the pressure and the volume increase with rising temperature. Now, if you take a gas and you cool it at sufficiently low temperatures, and if the pressure is sufficiently high, we'll see that later, you form a liquid phase, which is similar to a gas in that it doesn't have a fixed shape. The atoms are moving around, but they're weakly bound. And as a result, you form a phase called a liquid, which is almost incompressible, which means under reasonable pressures, it maintains a constant density. The volume of a chunk of a given amount of liquid is pretty much fixed. In both cases, in both phases, the density decreases with temperature. What that is especially useful to us for is it tells us that if you have a collection of fluid under gravity, then the warm fluid, which is expanded and is therefore less dense, will rise because it floats above the cooler liquid. And this brings us to the point that in equilibrium with gravity, the pressure in a collection of fluid will not be constant and the same at all points on the container. This is the case in the absence of external forces. In the presence of an external force like gravity, pressure will in fact increase with depth at a rate proportional to the density of the fluid. And let's see a demonstration of this, and maybe it'll help us understand what's going on. In this image, what we see is very simply me holding a slinky, a spring. And what you see when you look at it is the following not very surprising fact, which is that near the top of the spring is more stretched than it is near the bottom. And the way you understand that is quite simple. A slinky stretches more the more you pull it, and the top half of the slinky is holding up its own weight, as well as the entire half weight of the bottom half of the slinky, whereas the coils of the slinky very near the bottom are not holding up anything, and so they're relatively relaxed and unstretched. The higher up the slinky you go, the more of the weight the slinky is supporting, and therefore, if you look at it carefully, you'll see that the degree to which the slinky is stretched decreases uniformly from top to bottom. What we see here is me holding a cup of water. Now, this is to demonstrate the decrease in pressure with height or increase in pressure with depth. Now, this is true for the air. We know that at high altitude, air pressure decreases, but remember, the decrease in pressure is due to the extra weight of the air, and since air is not very dense, we're going to assume that air pressure is the same everywhere in this room. Not so for the cup, because the density of water is much larger. The water at the bottom of the cup, just like the spring at the top of the slinky, is holding up all of the water above it, whereas the water at the top of the cup is not holding up anything. And so I expect the pressure to increase from the top of the cup towards the bottom, respectful of the density of the water in the cup. And there's a way to see this. The way you see this is we drilled holes in the edge of the cup, and when I open those holes, if the pressure in the fluid is identical to the pressure at the top, which is the pressure of the air around it, then the fluid will happily stay in the cup held in by air pressure. But of course it won't. When I remove my fingers, the fluid will come splashing out, impelled by the excess pressure at the bottom of the cup relative to the air pressure, which is similar to the pressure at the top of the cup. And in case you're not certain that this is due to the weight of the water and to gravity, I will drop the cup, at which point fluid becomes weightless. The pressure at the top of the cup and at the bottom of the cup are now the same, and indeed the fountain ceases. So I hope I've convinced you that in a fluid in equilibrium under the influence of gravity, pressure increases with depth, depending on the density of the fluid. This is going to be important in astronomical context in understanding the structure of things like planets and stars, which contain fluid and are certainly held together by gravity. We talked about gases and liquids. Matter comes in a solid state. In the solid, the positions of atoms are roughly fixed. They can oscillate about those positions. This allows a solid to maintain its shape under external force. You can apply pressures and stresses, and a solid will react, but only a little bit. It will not, in fact, change its shape to suit a container. The slinky we had was a very good example of a solid object. It deformed in response to gravity, but it didn't completely stretch out. It gave some small proportionate response to the stresses that were placed upon it, And the larger those stresses, the larger the response, but the response was limited. The slinky retained, fundamentally, its shape even under duress. In all of these phases, fundamentally the interaction is between each atom or molecule and those near to it. There is no long distance interaction, or there's a weak interaction between atoms on one side of the slinky and on the other. Each bit of the slinky knows about the bits around it, and the result is that if you, for example, compress the slinky at one point, or move it at one point, then the perturbation travels through the material as each piece communicates the information, if you wish, to the next bit over, and these mechanical deformations of a solid, a liquid, or a gas are called sound waves, and they travel with a speed characteristic of the material. Now, the most familiar to us, of course, are the longitudinal sound waves in air. That is what we hear with our ears. But let's use that slinky as a very nice demonstration of wave propagation. To do that, let's see what happens when I let go of the top of the slinky. Remember, the slinky was extended in such a way that it was in equilibrium. The net force on every bit of it vanished, and this had to do with the fact that it was more extended at the top and less at the bottom, so that this compensated for the pull of gravity on every individual piece. Now, when I release the top of the slinky starts falling down, but near the bottom everything is still in equilibrium. The bottom of the slinky is not falling. What we see is a density wave propagating at the appropriate speed determined by the slinky through the slinky, and it is only when this wave reaches the bottom of the slinky that the bottom begins actually to fall. Until that time, it is in equilibrium, and the information that something has happened at the top has not reached it. What we're seeing is a sound wave. You bang on something at one point, and it takes time for that deformation to propagate through the material and reach the other end. In this simulation, we are going to be able to make some waves. So if I grab the end of this rope, the disturbance travels at the characteristic speed of sound down the rope. And frequently, we deal not with random perturbations, but with periodic oscillations, usually in a sine wave pattern, as is done here. Each point on the rope is oscillating periodically, and they're all oscillating with the same frequency, which is the frequency that this motor is oscillating with. In this case, it's oscillating with a frequency of 50 something, and so frequency F is the number of oscillations per second. And so it's measured, since this is a number, in units of inverse second, and once per second is called a hertz, which is why the frequency of your radio signal is measured in megahertz if you're listening to FM radio. And so I can restart this oscillation, and what we see is that because it takes a longer amount of time for the wave to get farther down the string, the position of the string here reflects what happened here a longer time ago than the position of the string here. And so the periodic oscillation of the driving force causes each point on the string to go up and down. Notice the wave is moving, the string is not going anywhere. But also what it causes is, because distance translates to time, we get a periodic sinusoidal structure in space at any given instant. And that is characterized typically by the distance between subsequent peaks, the distance along which the wave repeats. That's its wavelength lambda. And if you think about it, sitting at some point for a second, F peaks will come by, and so F peaks will come by. That means the wave will have transferred a distance of F times the distance between peaks. In other words, F times lambda is how far the disturbance travels in a second. So F times lambda is the speed of the wave, which we characteristically call c. Now, the reason we're dealing with periodic oscillations is a complicated mathematical theory called Fourier analysis that says any deformation can be written as a sum of periodic ones, but Fourier analysis is not some abstract mathematics. It's exactly what our ear does. When your ear hears sounds, it analyzes them into a sum of harmonics, and you hear the pitch of a sound you hear is given precisely by its frequency, and you can hear three different notes and distinguish that there are three notes there. This is biology and not physics, but it is definitely true, and I can increase the frequency, and what we see is that when I increased the frequency, the wavelength became correspondingly smaller. The frequency times the wavelength is a constant, the speed of the wave. A wave is characterized therefore by its frequency or its wavelength, given the speed, those are related, but also by an amplitude. An amplitude is simply the magnitude of the largest deformation. So an amplitude of 17 is a very small deformation, and an amplitude 3 times as large is a very large deformation. So periodic disturbances, as we saw, are characterized by their frequency f in hertz, the number of cycles per second. If a wave is traveling at a speed c, a periodic disturbance will produce a periodic wave in space at any given instant with a wavelength lambda that is related to the speed by this important relation. Lambda wavelength times frequency is equal to the speed of the wave. The wave is characterized also by the amplitude, which is the amount, the maximum amount of the perturbation. And one of the important things about waves is the string didn't move, but clearly waves carry energy from one place to the other. You can imagine hooking something at the other end of the string. I will vibrate this end, the wave will carry it and cause that object to vibrate, giving it kinetic energy. That kinetic energy came from my hand, and therefore a wave carries energy. In fact, it carries an energy, if it's periodic, per unit time that is constant. Over time, energy is flowing down the string, and so you measure an energy flux in joule per second. A joule per second is known as a watt. This is the same unit of energy per unit time that you measure the intensity of your light bulbs in. How much energy does it take to operate that light bulb for a second? Now, this is a wave on a string. Of course, a wave, like a sound wave that travels in 3 dimensions, will carry an energy flux that is a density, because if the wave is propagating over a wide front, each bit of the wave carries an energy. So we measure the flux in watts per meter squared of wave front, and that energy flux in watts per meter squared is proportional to the square of the amplitude. Clearly, the larger the amplitude, the more energy the wave is carrying, and the flux is going to be measured in watts per meter squared. Now, what happens when two waves meet is a very important property of waves. Let's look at it in a demo, and then we'll talk about it. In this demo, we have a loudspeaker. The loudspeaker will be creating a periodic wave, and we see the wave fronts are shown in this picture. They spread away from the loudspeaker, and what we see here is a measure of the pressure or the density, the perturbation that the wave represents at one given point, and we see the characteristic periodic oscillation that we're talking about. And one thing you can see is that unlike waves on a string, we'll talk about this, but because these waves are spreading out, the amplitude of oscillation is larger near the source than it is far, and anybody who's stood very near a honking car horn is painfully aware of this fact. We'll talk about that aspect of things in a little bit. I just thought I'd point it out while we're seeing it. But the interesting thing to note is what happens when instead of one loudspeaker, we put 2 speakers. So now the 2 speakers are both creating wavefronts, and we see here what happens as the wavefronts add. And you notice that I've put my detector in a very interesting point. The 2 speakers together, each of which would have produced the noise with the amplitude we saw before, produce essentially 0 noise at the position of this detector. But if I move the detector a little bit, I will see that it's not because the 2 speakers are not producing noise at all. I see that indeed at this position, they're producing a far louder noise together than either one separately, or in fact, more than twice the sound that each would have produced separately. Somehow the combination of the 2 speakers is focusing sound into these regions where the dark bands are, and leaving these regions where the gray bands are, the nodes, where essentially no sound gets to. Now, the reason that this is possible is because waves can subtract from each other. When these 2 waves propagate, it turns out they essentially don't interact with each other at all. That's the approximation that we're working in, and it's a valid one for sound waves. And what that means is that the total perturbation at any point in space and time is the sum of what it would be if there was one speaker and what it would be if there was the other speaker. And how does that, adding what one speaker would produce to what the other speaker would produce, lead to zero? Well, remember, they're both oscillating at exactly the same frequency. So there can be a point where, because of the time delay from this speaker being different from the time delay from that speaker due to the difference in distance, when a peak from this speaker reaches, it is always timed to arrive at the same time as a trough from this speaker, so that the two waves that these two create are always counteracting each other. Waves add, but that addition can amount to subtraction, and that phenomenon is known as interference, and it's characteristic of waves. So let's summarize what we've learned here. A hallmark of wave behavior is that waves are deformations or perturbations to some equilibrium, and when two waves meet at the same point in space and time, the two disturbances add. In other words, each wave behaves as though the other were not there. We just add the disturbances. What this allows, if the waves are of the same frequency, is that if the time delay between one source and the other source relative to your position is suitably adjusted, in other words, the distance difference, which translates to the time delay, is suitably adjusted, you can adjust it so a peak from one wave precisely meets a trough from the other. The two waves add in the sense that they subtract, and you can get nodes, you can get regions of quiet in the vicinity of two speakers producing the same frequency. This will be important to us. It's a hallmark of wave behavior. Now, another property of waves that is going to be useful to us is extremely useful, in fact, is something called the Doppler effect. It's the well-known phenomenon that the sound from a moving source sounds different than the sound from a stationary source. If a source of noise is approaching us, it sounds higher in pitch than were it stationary. If it's receding, if it's moving away from us, the pitch sounds lower. The archetypical example of this is the sound of a race car driving past you. I'll play it in the speakers, perhaps you can hear it. That whine is the transition from an elevated pitch as the car approaches you to a decreased pitch, decreased frequency as the car recedes from you. And the mathematical formulation of this is due to Doppler in the 19th century, and we can understand this rather straightforwardly. Here is a source producing regularly spaced periodic waves, and an observer placed over here receives the waves with a time delay. It takes time for each wave to reach there. The time delay is the same for each wave, so the time between subsequent fronts is the same as the time between subsequent emissions. And this is a stationary source. The frequency with which his ear is oscillating is the same as the frequency with which this source is producing the sound. That is true. Now let's move on to the case where the source is moving, and let's again place our observer over here, and we see that what's going on is that the wavefronts appear compressed on this side. They're compressed, of course, because between the emission of one wave and the next, the source moves, and so the distance between the wavefronts, as seen by the observer here, is smaller than it would be were the source stationary, and we can easily compute the relation between the two, because the distance between subsequent wavefronts as they arrive at this observer, lambda, which is the wavelength that this observer sees, is equal to the distance between the two wavefronts when they were emitted minus the distance which the source traveled, because each subsequent wavefront has a shorter distance to travel, because in the interim between emitting one wavefront and the following, the source traveled a distance given by v times the time between wavefronts. What's the time between wavefronts? The time between emissions is 1 divided by the frequency, because this is a number of seconds. And so remembering that lambda times f is c, I can write f as c over lambda, and I get lambda is lambda 0 minus, let me write this correctly, lambda is lambda 0 minus v lambda 0 over c, or Doppler's formula, lambda is lambda 0 times 1 minus v over c. Notice that this v was taken to be positive when the source was approaching the observer, an observer on this side, of course, sees the wave dilated. The wavelength looks longer, the pitch is lower as the car is receding from you. Each subsequent wavefront has a longer distance to go. That is compensated in this formula by considering V to be negative if the source is receding and positive if the source is approaching you. We talked about heat energy, and we need a few properties of heat because heat will be a dominant form of energy in some environments that we talk about. And so it's a property of heat that if you have a hot object and a cooler environment, then the hot object will lose energy to the environment, and this process will continue indefinitely or until such time as the temperatures equilibrate, because as the source loses heat, the environment gains heat and warms up, and eventually, if the temperatures are equal, then we have equilibrium and heat flow stops. But so long as you have a warm sun in cold space, the sun will continue to lose heat to space, and until such time as either space heats up or the sun cools down, this process will continue. There will be a constant flux of energy out of the sun into space. And there are several ways by which this transfer of heat from a hotter to a cooler body can occur. One is called conduction. This is where heat is transferred through continuous contact, and this is not in great importance. In astronomy, heat conduction on astronomical scales is rare. A second phenomenon is convection. This is basically like trucking. This is what happens when the physical motion of the fluid carries energy. This works very well if you have a volume of fluid that is heated from below. That happens when you boil water on your stove. It also happens in stars, say, where a hot core is heating the atmosphere from the inside. What happens is that at the bottom of the pot or the bottom of the atmosphere, the fluid is heated. The heated fluid expands. The expanded heated fluid is lighter, less dense than the surrounding fluid. It therefore floats to the top and rises. Cooler fluid descends to take its place. And what you have is an energy transfer from the bottom to the top by heated fluid physically moving from one part to the other. And this does occur in astronomical phenomena. None of this, of course, is helpful to the sun in losing its energy to space, because the sun is not in contact with anything, nor is there any fluid around it to convect. The way the sun loses energy to space is radiation. It turns out that every object, unless it's at zero temperature, glows, and that mechanism of energy loss is radiation heat transfer, and essentially the radiation in question is sunlight. Sunlight is the way the sun attempts to heat up space, losing energy because it's warmer, and we'll come back to this calculation in a moment, but let's understand something about this heat flux, energy flux problem. And so the sun is hot, and so it radiates, and we'll learn how to compute how hot it is and how much it radiates. But for now, let's assume that the sun is radiating energy at a constant rate. Why is the rate constant? Because the properties of the sun are unchanging, the properties of space are unchanging. So the rate at which the sun loses energy to space is therefore unchanging. We call that rate the luminosity, and it's measured in joules per second, in watts. The sun, like a light bulb, produces a certain amount of energy, or loses a certain amount of energy to space every second, and we'll figure out this number. Obviously, it's a great many light bulbs. Now, what interests us often is how bright the sunlight is at some given location in space, and what that implies is put some uniform detector, say an eye with a fixed surface area, and as we saw, or as this diagram shows, if this is something the size of your eye or of your detector, the farther it goes, the less sunlight it traps, because essentially the sun produces radiation in all directions, and so at any distance, the sunlight is spread uniformly across the surface of a ball or a sphere of radius r. And if you are at some distance and you place your detector takes up some fraction of that sphere. If you are twice as far, the sphere is larger, and your detector now takes a smaller fraction of this larger sphere, and the result will be that your detector, since all of the sun's rays pass through this sphere, and all of the sun rays a little later pass through this sphere as well, the net total amount of energy passing through each sphere is the same, but the total amount passing through a fixed detector decreases because the spheres grow larger, whereas the detector does not. Mathematically, the statement is that at a distance r, the radiation is distributed uniformly on the surface of a sphere, so energy per second received by a square meter of detector will be the luminosity divided by the surface of a sphere across which the radiation is spread uniformly. And so the sun energy is diluted by a factor of r squared as it travels out into space. Light, of course, is going to be of incredible importance in our understanding of the universe. It's the main way we perceive our environment on Earth. It is certainly the main way that we receive information from distant places in the universe, so the properties of light will be extremely important to us. So light, of course, is the main way we as humans perceive the world around us. It's also the main way that we as astronomers learn about distant objects. The nature and the properties of light are going to be extremely important to us. And the first of these is the speed. So light carries energy away from the sun to Earth to warm us. And the speed at which light propagates is huge. It's about 3 times 10 to the 8th meters per second. This large number makes accurate measurement difficult. First really good measurement was in 1850 by Foucault and Fizeau, though there were earlier less precise measurements. Now, in a classic experiment in 1670, our old friend Newton made the discovery that the sunlight, white, colorless light from the sun, in fact contains all colors of light. He found a way to split a beam of white light into beams of various colors. He was using a prism. Today we use a diffraction grating. And he conjectured that the nature of light was a stream of particles. Of course, he had all the mechanics know-how to understand a stream of particles. Light moved in straight lines, like particles upon which no forces act, moved at a constant velocity. It seemed a lot like a mechanical particle model of light would be likely. This is one of the rare cases where Newton was wrong, because in 1799, only 120 years later, Young observes light waves interfering. So he makes the observation that you can take light and you can construct these interference effects where light waves add and subtract and you get nodes. This interference was a hallmark of wave phenomena, so Newton for once was actually wrong. Light is a wave. But never count Newton out. We'll come back to this point in the next clip. And that same Young, 3 years later, shows that our eyes, while they are extremely accurate in giving directional perspective, so they tell us very precisely which direction light is coming from, that's how we construct our image of the world, are in contrast relatively poor as Fourier analyzers. Unlike our ears, which can distinguish a great variety of sounds and hear several simultaneous tones and distinguish them, our eyes are a very poor Fourier analysis machine. They only are sensitive to the relative intensity of 3 colors, red, green, and blue, and we'll see in a minute what that leads to. What we're going to do is an experiment somewhat similar to what Newton did. So we have here a beam of white light, and we're going to put a diffraction grating in front of it, and the diffraction grating splits the white beam so that the white stripe in the center is somewhat dimmed, and on both sides we find the familiar rainbow structure. And so we see a stripe of red flaring to orange and yellow and green and into blue and violet. And we can see what happens when we put a filter in front of the light. We get red light, and when we feed red light into the diffraction grating, what we see in the spectrum is that the green and the blue are missing. Similarly, when we feed green light into the diffraction grating, the blue and the red are missing and only green light comes in. So the diffraction grating is not coloring the light, it is deflecting whatever green light it gets to that region. Again, putting a blue filter in front of the beam, we see that only the blue remains in the spectrum. The blue filter absorbs the green and the red, the green filter absorbs blue and red, and the red filter absorbs green and blue. These are, it turns out, the primary colors. It has to do with our eyes. Here's what happens when you put a cyan filter in front. A cyan filter absorbs the red light and so lets through the blue and the green. Similarly, if we use a magenta filter absorbs the green, letting through the blue and the red. So what we see as magenta is blue light and red light. There is also, we can put a yellow filter in, and this is important. We see that what we perceive as yellow light is, in fact, light that is missing its blue. The green and the red are present, the blue is absent, and we see yellow. And so if we superpose the yellow and the magenta filters, the yellow filter absorbs the blue, the magenta absorbs the green, and what is left is red. And indeed, superposing those two filters, we get red. If we superpose yellow and cyan, the yellow absorbs the blue, the cyan the red. What's left is the green, and we see that very nicely in this picture. And we can keep playing. We can superpose the cyan and the magenta. The cyan absorbs the red, the magenta absorbs the green. Putting them on top of each other, we're going to be left with blue. So this has to do with the way our eyes see colors. The important thing for us to take away here is that a filter that absorbs the blue looks yellow. We cannot distinguish this yellow from the yellow in the spectrum there in between the red and the green that is pure yellow light. We saw that, as Young showed us, light is a wave, and also as Young showed us, our eye, in fact, has 3 color detectors, one sensitive to red light, one sensitive to green light, and one sensitive to blue, and what we perceive as color is merely the relative intensity at which those 3 detectors are excited. So yellow light that excites the red and the green approximately equally, because in the spectrum, yellow light is between red and green, cannot be distinguished from a combination of actual red and green light. And so our eye, unlike our ear, is not a very good Fourier analyzer. So much for biology, but this will be important in understanding some phenomena later. And then, once we know that light is a wave, it's not too shocking that color is a property of the wave. Color turns out to be the frequency of light. Visible light has a frequency of order 10 to the 12th hertz. Even at the rather high speed of light, we can compute the wavelength is pretty short. It's between 400 and 700 nanometers. A nanometer is a billionth of a meter, 10 to the minus 9 meter. And these are the units in which typically we measure the wavelengths of visible light, at least in astronomy. And so 400 nanometers, the shortest wavelengths, visible light is the blue light, as this indicates, and the red end of the spectrum is the longer wavelengths, and the order of the colors in the rainbow is according to their wavelengths, so that violet light, in fact, is at the short end of the spectrum, green is somewhere in the middle, around 550 nanometers is green light, and so on. Now, for something completely different. We talked about gravitation as the force that dominates astronomy, but in most of our lives, gravitation of the Earth is important, but when we interact with each other or with objects around us, gravitation is completely unimportant. The gravitational force of a human being is negligible compared to the other forces we interact with. The force that turns out to dominate most of physics is electromagnetism, and so we need to understand some things about this. And the simplest version of electromagnetism is the force between 2 static charged objects. So there is in the universe a thing called electric charge. Some objects carry electric charge. You can charge your hair by combing it on a dry day. And the annoying force that makes your hair stand on end on a dry day is this electrostatic or Coulomb force, which has a formula that will appear familiar. The force between 2 objects of charges Q1 and Q2 is given by a constant times the product of the charges divided by the square of their distance. This might appear familiar. It's that square of the distance again. It's not exactly a coincidence. The big difference between electric charge and mass, or between Coulomb's law and Newton's law, is that Newton's law, remember, had F equals G m over r squared. And these numbers were positive and the force was attractive, always. Gravitation is a universally attractive force. Coulomb interactions can be attractive or repulsive. It turns out that the force is attractive when the 2 charges are of opposite sign, so positive and negative charges attract. and charges of like sign repel with an equal magnitude, but the sign, the direction of the force, depends on whether the charges are equal or opposite. This in turn explains why this force does not dominate the universe and this force does. It's not because gravitation is stronger. In fact, we have an invariant measure of strength under which gravitation will be a far weaker force than electromagnetism, but because opposite charges attract, most objects are neutral. In the presence of charge, if you have something that's charged positively, it will attract negative charge until such time as it reaches equilibrium, in other words, is neutral. This is not possible for mass. There is no concept of negative mass. In fact, it's worse than that. We'll discuss the instability of gravity. This will have profound consequences, so I'm not just belaboring an obvious point. And charge, like mass, momentum, energy, etc., is conserved. You can neither create nor destroy charge, though, of course, charge can be transferred from one object to the other. So when you comb your hair, the comb is charged with one charge, your hair with the opposite charge. When atoms form an ionic bond, they exchange charges and so on. But the total charge in the universe, or in any enclosed region in the universe, is conserved. And then, you see, in gravitation, I kept wanting to talk not about the gravitational force, but the gravitational acceleration. So you talk about the Earth, for example, generating around it a gravitational field. The gravitational field is the statement that were a mass to be placed there, it would experience a force. And you can compute the force per unit mass without knowing what the size is of the mass that you would introduce. And in a similar way, you talk about an electric charge producing an electric field, which is the force per unit charge that would act were a charge to be placed there. So a charge creates an electric field around it, because another charge, were it to be brought there, would be affected, and a charge is affected by an electric field. A similar phenomenon of a field, a region around an object in which other objects might be impacted, is encountered with magnets. A magnet creates around it something that we can call a magnetic field. In the presence of such a field, any other magnet, like this little compass, will align itself in a particular direction at any given point in space. Of course, it will align itself so that its north pole faces the south pole, and so on. And so we can imagine that this region of space has some property called a magnetic field, which is the statement that were you, remember there was a field here even before I brought the compass, that told you that were you to bring the compass, it would point in such and such a direction. Now, magnets and electricity initially appear completely unrelated, and it is known, however, that electric currents, in fact, produce magnetic fields. In the vicinity of an electric current flowing around a coil behaves very much like a magnet. We call this an electromagnet. And we see that we have a magnetic field in the vicinity of an electric current. Moving charges create magnetic fields. So this is the first relation between electricity and magnetism, but there is another relation, which is that if you have a changing magnetic field, it will cause charges to move so that this magnet has absolutely no impact on the charges in this coil. But if I move the magnet so that the magnetic field in the coil changes, then while the change is ongoing, current will flow, and current flows means there's a force on these charge carriers. This implies an electric field. A changing magnetic field causes an electric field, and I can, of course, cause the change by moving either the magnet or the coil. And so changing magnetic fields essentially can be thought of as generating electric fields. This has profound consequences. Let's see what they are. The fact that moving charges can create a magnetic field was discovered in 1820 by Ørsted, and it turns out that moving charges are also affected by magnetic fields. We saw that when we moved the coil in the presence of a magnetic field. Faraday realizes the phenomenon that we were discussing, which is that a changing magnetic field is tantamount to an electric field. 30 years later, Maxwell writes down what are the collected set of equations describing electric and magnetic fields, and in particular the phenomenon he needs to add is that a changing electric field creates a magnetic field. In the presence of a changing electric field, there's a magnetic field. And the combination of these two phenomena leads in Maxwell's equations as part of the solutions to propagating waves. Propagating waves in which essentially you set up a changing electric field which creates a magnetic field, which creates an electric field, which creates a magnetic field. You solve the differential equation that this leads to, and you find that it describes a propagating wave, and Maxwell computes from the properties of magnets and currents and Coulomb's law, properties that had been measured in the lab. He can compute the velocity of these waves that he's discovered, and their velocity, surprise, surprise, is precisely c. He didn't get it this precisely, but it coincides with the speed of light that Fizeau and Foucault had measured 11 years previously. So Maxwell has very good reasons to imagine that he's discovered that light is a wave, as Young said. In fact, we now know what it is a wave of. It's an electromagnetic wave. The disturbance that propagates in space when a light beam travels through it is an electromagnetic wave, is a disturbance in the electric and magnetic fields, which have come to take on sort of a life of their own. Remember, they were ways to calculate what would happen if you put a charge, and suddenly they create each other and they propagate through space far away from the charges that might have created them in the dim, distant past. They have essentially their own existence. And so we do talk about these fields as important objects. The understanding that light is an electromagnetic wave also tells you that you can, in principle, imagine oscillating a charge or creating an oscillating electric field at any wavelength or any frequency. So we know that we see light from between 400 and 700 nanometers in wavelength. What about the solutions to Maxwell's equation with wavelengths outside this region? And it turns out that there is an entire huge electromagnetic spectrum out there, ranging from, at very high frequency and very short wavelength, gamma rays with wavelengths of down to 10 to the 14, 10 to the 15 meters and below, except below that are very hard to produce, through the X-ray spectrum that runs from wavelengths of about 10 to the minus 9 to 10 to the minus 12 meters, and then the ultraviolet light, which is the chunk of the spectrum immediately beyond the deep violet light at 400 nanometers, that is the shortest wavelength our eyes can see. And then on the other side, to the left of the red light, we have infrared light, and below that, microwaves and radio waves, whose wavelengths can be hundreds of meters. And so there's this entire spectrum, and in fact, we're familiar with it, we use it. Our eyes are sensitive only to this tiny little bit of the electromagnetic spectrum. Our eyes have all kinds of inefficiencies, but in this case, our eyes are well adapted to where we live. If you look down here at the bottom of this plot, this is the transparency of the atmosphere, and you see that, for example, gamma rays and X-rays are not very useful, despite Superman claim to the contrary. X-ray vision is not very useful because X-rays are very quickly absorbed in the atmosphere. They do not penetrate. Visible light penetrates the atmosphere. A little window in the infrared penetrates the atmosphere. And then radio waves penetrate the atmosphere. Well, we know that because that's how we watch TV. But the wavelengths of radio waves are too long. You would need your eyes to be antenna. They would need to be on the order of meters in size. We do not have eyes meters in size. There would also be other limitations. It would be hard to see features of the universe smaller than a few meters across. So given our need for fine resolution, our eyes are well adapted to the conditions under which we evolved. But the universe, on the other hand, produces light across the entire spectrum, from high-energy gamma rays to radio waves, and it's important, in order to collect information about the universe, to be able to observe it in all possible frequency bands. And indeed, with technology, people have developed ways to observe the universe in all of these frequencies, and at every time that we've developed a new technology and a new way to look at the universe, there have been new and often surprising discoveries made. Note that observations in many of these bands, in the ultraviolet, in X-rays, and in gamma rays, for example, need to be made outside the atmosphere, putting a very good gamma ray detector on the ground will not buy you anything because gamma rays from space will not penetrate. So these observatories, including actually infrared observatories, tend to be space-borne or at least high-altitude balloon flights. Radio telescopes can be placed on, are placed on the ground. Those are these very large dishes that receive radio waves, and over the course of the class we will have occasion to use information collected by all of these bands. So it's the richness of the spectrum corresponds to the richness of phenomena out there. We're almost done with our discussion. One last statement now that we have our understanding of the spectrum. A hot object radiates. That's what we discussed. Everything radiates, as long as it's warmer than the surroundings. For a dense, dark object, so for an object that essentially absorbs light that hits it, such as you, me, the Earth, and it turns out the sun, the radiation is almost completely characterized, and it's precisely completely characterized for some idealized black body, an object that absorbs any light that falls upon it, by the temperature. It turns out that the nature of the radiation produced by a warm object, if it's dense, is essentially a property of light and thermodynamics and has nothing to do with the object itself. And this is called blackbody radiation, and it has two important properties. One is that hotter objects are blue. This despite the fact that blue is a cold color and red a warm color to our intuition. It turns out that hotter objects radiate shorter wavelength. In other words, a blue glow is hotter than a red glow because a red glow has a longer wavelength. This is summarized in Wien's displacement law, which says that the wavelength at which an object emits more radiation than any other wavelength, the wavelength of maximum emission, multiplied by the object's temperature, is actually a constant, so that if you double the temperature of an object, the wavelength at which it emits is halved, and Wien's constant is written over here. It's got units of meters times Kelvin, so wavelength times degree. The other and more familiar statement is that hotter objects produce more light. This is encoded in the Stefan Boltzmann relation, which tells us that the rate at which each meter squared of an object radiates, of course a big object radiates more than a little object if they're the same temperature. 2 light bulbs make more light than 1 light bulb. So we need to normalize to the rate at which an object produces radiation per meter squared, that's F in watts per meter squared, and the rate at which each meter squared of an object radiates is proportional to the 4th power of the temperature in degrees Kelvin, and so doubling the temperature leads to a 16-fold increase in radiation, and the constant, the Stefan Boltzmann constant, sigma, has this numerical value in our units, and its units are watts per meter squared per degree Kelvin to the 4th. Let's take a look at what this black body radiation looks like. Here we have a plot of the relative intensity in various wavelengths as a function of the wavelength from near zero to a few times 10 to the minus 6 micrometers, and so the visible band is located over here, and the black body curve has this characteristic shape. As I said, it's independent of the material, and the curve I've plotted here is the curve for an object that glows that has a temperature of about 3,000 degrees Kelvin. 3,000 degrees Kelvin is about the temperature of the filament in an incandescent light bulb. And what you will notice is that most of the light produced by an incandescent light bulb's blackbody radiation is in fact not light. It is invisible to us. It is infrared radiation which heats us. If you understand, if you talk about people not liking incandescent lamps as being very inefficient, this is because due to limitations of the filaments melt if you heat them too hot. Most of the light produced by an incandescent lamp is in fact not light, it is just heat. And so, on the other hand, if we heat the object a little bit, this is an object with a temperature of, say, 6,000 degrees. This is closer to the sun, and you see that much of the light produced by the sun is in fact in the visible spectrum. It's very nice of the sun to be adjusted to our atmosphere so that much of the sunlight can in fact penetrate our atmosphere and we can use it to see. And you also see that the factor of 2 in temperature leads to this huge increase. The previous light bulbs graph has been scaled down here. It looks very small. Remember, doubling the temperature increases the total radiation by a factor of 16, and it has also moved the maximum from, according to Wien's law, from the infrared, in this case, down into the visible. And we can add another object, say, with an even higher temperature. Let's say 12,000 degrees, so another doubling. In this case, the spectrum, again, increases to the point where the sun spectrum is negligible, and the peak is now in the ultraviolet. So we're seeing Wien's displacement to the left. Hotter temperatures mean bluer light. We're also seeing the Stefan Boltzmann law in action. Hotter temperatures mean way, way, way more light. These are all important observations. Let's see what we can do with them. That was a long video clip. There was a lot going on there. We got to go through 2.5 centuries of physics. Remember, what we're doing is we're packing our toolkit so that we know what it is we need to address understanding astronomy. So don't despair. Rather than trying to summarize all the disparate things we talked about, let me do an example of an application to actual astronomy of what we learned about that might clarify some things. So let's talk about the sun. We said that the sun radiates its heat. Let's see what all our various results tell us about solar radiation. So we can measure the brightness of sunlight on Earth in watts per meter squared. How do you do that? Well, put out a meter squared of detector and measure how much sunlight hits it. Put out a meter squared of something very dark that absorbs all the sunlight. Measure how much energy that thing receives, and you find the number is called the solar constant, and it is 1,361 watts per meter squared. So a meter squared of sunlight will run a very small hairdryer or light 10 incandescent light bulbs. So we know the intensity of solar radiation in the vicinity of Earth. Now, we know how far the sun is. The sun is 1 astronomical unit, or 150 million kilometers away. And so if we know how bright it looks and we know how far it is, we know that we can compute its luminosity. Remember, we had that B, the brightness, is the luminosity divided by the area of the big ball, whose radius in this case is the distance to the sun, or 1 astronomical unit. And so we can solve this. We know the brightness, we measured it. We know the distance. We can write an expression for the luminosity, and it's 4 pi times the distance to the sun squared times the brightness of the sun. And so we put in the numbers. This is 4 pi times 1.5, I'm rounding, times 10 to the 11 meter squared times 1361. And we evaluate the calculation, and you find that the sun is a very bright light bulb indeed. It has a luminosity of 3.8 times 10 to the 26 watts. That's a lot of energy lost by the sun. Now, we can measure the radius of the sun. Since we know the distance, we can make a small angle calculation. We measure the angular size of the sun in the sky, and we find that the radius of the sun is 6.96 times 10 to the 8th meter. That's about 700,000 kilometers. And from this, we can figure out something else, because what we know now is that, think of the sun as a ball. Every square meter of the ball is radiating light to the outside. You count how many square meters there are on the surface of a ball. That would be 4 pi times the radius of the sun squared. If I multiply that by the flux, the amount of power in watts emitted by each square meter, this should equal L. Since I know the radius of the sun and the luminosity, the total amount of energy that's being emitted, I can figure out the flux that each square meter emits. Now, the luminosity, as I said, is the area of the sun times the flux, and so I could compute the flux. The nicest way to do this is to use a scaling relation as usual. So the scaling relation is going to be that I have that F, which is L over 4 pi times the radius of the sun squared, and I have that B is L over 4 pi times the distance to the sun squared. I can cancel everything around, find that L is B times the distance to the sun divided by the radius of the sun squared. And this relates again a flux to a flux through a dimensionless quantity. I recommend this method of computing, and this is 150 million, this is 700,000. That's a big factor. Every square meter of the sun produces 6.3 times 10 to the 7 watts. A square meter of sun produces 63 megawatts of light emitted out towards the universe. That's a large number, but we can go further. We have the flux, and we know the Stefan-Boltzmann law. We know that the flux is also equal to sigma t to the fourth, since the sun emits approximately as a black body. It's dense enough. And so, since we know the flux, we can compute the temperature, and we can actually find the temperature of the part of the sun that we see. It's called the photosphere. It's somewhere outside on the surface of the sun. And we find that the temperature is the fourth root of F divided by sigma. The temperature of the radiating surface of the sun, of the photosphere, is about 5800 Kelvin. I can use Wien's law, because I know the temperature, to figure out the wavelength of maximum emission for the sun, the wavelength at which the sun emits more light than anything else. I take Wien's constant, 0.0029 meters is the value of Wien's constant. I divide by the temperature of the sun, and I find that the sun produces more light than any other frequency at a wavelength of 503 nanometers. And if you look up the table, this is somewhere between the red and the blue, and indeed, it is green. But Ronan, you tell me, every kindergartner knows the sun is yellow. Yes, but not really. Every kindergartner knows the sun appears yellow. Why that is consistent with the maximum emission being green, we'll see in the next clip. In the meantime, go and catch your breath. We have gone through many, many different topics here. We have a whole grocery list of new ideas and new concepts to digest and to learn how to use, and we'll start applying those very soon.